Little Ada loves poetry and philosophy, but above all, she loves numbers. She doesn't think of anything else. A woman who knows about numbers in 19th century London? Unthinkable.
Augustus Ada King, Countess of Lovelace, was an English mathematician and writer, chiefly known for her work on Charles Babbage's proposed mechanical general-purpose computer, the analytical engine. She was the first person to recognise that the machine could be applied to tasks beyond pure calculation. Her work on this led her to publish the first algorithm intended to be carried out by such a machine, and as a result, she is sometimes regarded as the first to recognise the full potential of a computing machine and one of the first computer programmers.
As long ago as the 1840s, Lovelace envisioned machines that could manipulate symbols instead of just numbers. And while there are some who would debate her title as world's first programmer, there's no denying her influence as a gifted mathematician who was also way ahead of her time.
In the century before the first general-purpose computers, Ada Lovelace is often called the world's first computer programmer. Born Augusta Ada Byron in 1815, Lovelace was the daughter of famous poet Lord Byron, who, expecting the baby to be a glorious boy, was somewhat disappointed.
Her father was one of Britain's greatest poets, but her mother, hoping to steer her away from those dangerous poetic tendencies, made sure she received tutoring in math and music, and it worked.
Her parents soon separated, and Ada was raised by her aristocratic mother, who was so determined that her daughter not become a poet that she educated her in mathematics from an early age. As it turned out, Lovelace had an incredible affinity to the subject, helped by tutors like mathematician Augustus de Morgan. And at the age of 17, she was introduced to Charles Babbage, who was in the midst of developing his analytical engine, the theoretical precursor to the first computers.
In those days, computer was a person who did calculations, sometimes with the help of machines, but often not. This job title persisted until the late 1800s, when the meaning of computers started shifting to refer to devices. And notable among these devices was the step reckoner built by German polymath Gottfried Leibniz in 1694. With some clever mechanical tricks, the step reckoner was also able to multiply and divide numbers. Multiplications and divisions are really just many additions and subtractions. For example, if we want to divide 17 by 5, we just subtract 5, then 5, then 5 again, and then we can't subtract any more 5s. So we know 5 goes into 17 3 times, with 2 left over. The step reckoner was able to do this in an automated way and was the first machine that could do all 4 of these operations. And this design was so successful, it was used for the next 3 centuries of calculator design. Unfortunately, even with mechanical calculators, most real-world problems required many steps of computation before an answer was determined. It could take hours or days to generate a single result. Also, these handcrafted machines were expensive and not accessible to most of the population. Charles Babbage proposed a new mechanical device called the difference engine, a much more complex machine that could approximate polynomials. Polynomials describe the relationship between several variables, like range and air pressure, or amount of pizza Carrie-Anne eats and happiness. Polynomials could also be used to approximate logarithmic and trigonometric functions, which are a real hassle to calculate by hand.
It will be a party that calls the prejudice of the time into question. It's 1833, and between a drink and a dance, Ada meets a scientist named Charles Babbage. They talk about everything, or rather, they talk only about mathematics. Babbage is fascinated by it. He writes several letters to her, calling her the Enchantress of Number, and he immediately involves her in a project. A differential machine, able to perform arithmetic operations automatically. It may seem normal to us, but remember, we are in 1833.
Ada described her approach to science as poetical. Her mathematical talents led her to a long working relationship and friendship with fellow British mathematician Charles Babbage. She was particularly interested in Babbage's work on the analytical engine.
Ada was 17, Babbage was 42, but intellectually they were peers. But she continued to correspond with Babbage for the next 2 decades. Babbage's most notable invention was the analytical engine, a brass and iron steam-powered machine he first envisioned in 1837. It included a central processing unit called the mill and expandable memory, which he called the store. Controlled by punched cards, which could be used to input data, the engine could be programmed to carry out different mathematical operations.
It could be used for many things, not just one particular computation. It could be given data and run operations in sequence, it had memory and even a primitive printer. Like the difference engine, it was ahead of its time and was never fully constructed. However, the idea of an automatic computer, one that could guide itself through a series of operations automatically, was a huge deal and would foreshadow computer programs. English mathematician Ada Lovelace wrote hypothetical programs for the analytical engine, saying a new, a vast and a powerful language is developed for the future use of analysis. For her work, Ada is often considered the world's first programmer.
The engine behind me is Babbage's difference engine number 2, designed by Charles Babbage, an English mathematician who is also known as the first computer pioneer. Babbage designed this machine between 1847 and 1849. Babbage, as we know, did not succeed in completing any of his own engines in their entirety, so there is no complete Babbage engine. This is the first physical realization of any of Babbage's complete designs in the metal. The engine itself weighs 5 tons. It consists of 8,000 parts made of bronze, cast iron and steel, and it measures 11 foot long and 8 foot high. It's operated by cranking a handle. What it does is it calculates and tabulates the value of any 7th order polynomial, a class of mathematical expressions, to 31 decimal places. It not only calculates that with unerring accuracy, it also prints an inked hard copy as a record of the results, and also produces what are called stereotype plates. That is, it impresses the results in soft material, plaster in this instance, so that you can make a printing plate automatically. Now, the purpose of all this was to eliminate the risk of human error in the calculation and production of printed mathematical tables.
Babbage was impressed with Lovelace's intellect, calling her the enchantress of numbers, and he enlisted her help in translating the papers of Italian mathematician Luigi Menabrea on the analytical engine, as well as inviting her to add her own notes on the topic. Her notes were extensive, 3 times longer than the original paper.
They included some of Babbage's own calculations, at least some of which she found errors in and corrected, but to demonstrate the machine's possible applications, she also described how it could be used to calculate an arcane, brain-teasing sequence of figures known as Bernoulli numbers. She proved it by diagramming the computations that the analytical engine would make, which, believe it or not, looked like this. Essentially, she had written a computer algorithm. She also speculated that the device might be used beyond numbers and could be used to manipulate anything within a fixed set of rules. She said it could be used for both practical and scientific purposes, and it might one day compose elaborate pieces of music of any complexity or extent. Basically all the stuff that we use computers for today.
These notes contain what many consider to be the first computer program. That is, an algorithm designed to be carried out by a machine.
In her paper published in 1843, she also suggested that such a machine could be used to create complex music and graphics, as well as other practical uses in science. Though she died at the age of 36 in 1852, her predictions would later be proved correct. Today, her early contributions are recognized in the computer language named Ada, and through Ada Lovelace Day, a date that has now become a celebration of all inspirational female scientists and mathematicians.
And today, in St. James Square, London, she has her own blue plaque as a historical marker to her memory.
Lovelace's notes are important in the early history of computers. She developed a vision of the capability of computers to go beyond mere calculation, while many others, including Babbage himself, focused only on those capabilities. Her mindset of poetical science led her to ask questions about the analytical engine and examined how individuals and society relate to technology as a collaborative tool.
When I was a girl, I wanted to be a storyteller. I loved make-believe worlds, and my favorite thing to do was to wake up in the mornings in Moomin Valley. In the afternoons, I would roam around the Tatooines, and in the evenings, I would go to sleep in Narnia. And programming turned out to be the perfect profession for me. I still create worlds. Instead of stories, I do them with code. Programming gives me this amazing power to build my whole little universe with its own rules and paradigms and practices. create something out of nothing with the pure power of logic. Here's what I think today. Little girls don't know that they are not supposed to like computers. Little girls are amazing. They are really, really good at like concentrating on things and being exact, and they ask amazing questions like what and why and how and what if, and they don't know that they are not supposed to like computers. It's the parents who do. It's us parents who feel like computer science is this esoteric, weird science discipline that only belongs to the mystery makers, that is almost as far removed from everyday life as, say, nuclear physics. And they are partly right about that. There's a lot of syntax and controls and data structures and algorithms and practices, protocols and paradigms in programming. And we as a community, we've made computers smaller and smaller. We've built layers and layers of abstraction on top of each other between the man and the machine, to the point that we no longer have any idea how computers work or how to talk to them. And we do teach our kids how the human body works. We teach them how the combustion engine functions. And we even tell them that if you want to really be an astronaut, you can become one. But when the kid comes to us and asks, so what is a bubble sort algorithm? Or how does the computer know what happens when I press play? How does it know which video to show? Or Linda, is internet a place? We adults, we grow oddly silent. It's magic, some of us say. It's too complicated, the others say. This whole quest kind of led me to this little girl. Her name is Ruby. She's 6 years old. She's completely fearless, imaginative, and a little bit bossy. And every time I would run into a problem in trying to teach myself programming, like what is object-oriented design or what is garbage collection, I would try to imagine how a 6-year-old little girl would explain the problem. And I wrote a book about her and I illustrated it, and the things Ruby taught me go like this. Ruby taught me that you're not supposed to be afraid of the bugs under your bed, and that even the biggest of the problems are just a group of tiny problems stuck together. And Ruby she also introduced me to her friends, the sort of colorful side of the internet culture. She has friends like the snow leopard, who's beautiful but doesn't want to play with the other kids. And she has friends like the green robots that are really friendly but super messy. And she has friends like Linux the penguin, who's really ruthlessly efficient but somewhat hard to understand, and the idealistic foxes and so on. You learn decomposition skills by problem-solving flowcharts and seeing what went wrong in Ruby's friends' practicalities. You learn that algorithms, they are really much like cupcake recipes. And most of all, you learn that there are no ready answers. Imagine a world where the little Ada Lovelaces of tomorrow, who live in a permanent reality of ones and zeros, they grow up to be very optimistic and brave about technology. They embrace the powers and the opportunities and the limitations of the world. A world of technology that is wonderful, whimsical, and a tiny bit weird.